Hello! Today, we're going to dive into AP Precalculus, topic 1.14, Function Model Construction and Application. By the end of this lesson, you will be able to construct different types of functions, polynomial, piecewise, and rational, to model real-world situations, and then use those models to answer specific questions. This means we'll be looking at situations, figuring out what kind of function describes them best, and then using that function as a predictive tool. Let's start with learning objective 1.14. A. Constructing polynomial and piecewise models. This objective has a few parts. We'll learn to construct models based on polynomial families like linear, quadratic, cubic, or quartic, based on restrictions from a problem's context. We can construct these models in a few ways. First, we can use context clues, like the zeros, intercepts, symmetry, or turning points in a situation, to determine the degree of the polynomial. This means we can look at a problem and identify clues that suggest it follows a certain type of polynomial curve. Second, if the situation is a transformation of a parent function, like a parabola that's been stretched and moved, we can construct the model using those transformations. Third, we can use technology like graphing calculators to perform regressions on datasets, which fits a polynomial curve to the data. We'll check the regression residuals to see how good the fit is. This is a powerful tool when you have real-world data points and need to find a function that best represents them. Finally, we can construct piecewise defined models when a situation's behavior changes over different intervals, using combinations of these modeling techniques. Piecewise functions are for situations that don't have one simple rule, but follow different rules depending on the input. Let's work through an example of constructing a polynomial model. Imagine a diver jumps off a 20-foot platform. After 1 second, they are 12 feet above the water. Let's model the diver's height over time. We can represent this situation with a polynomial function. First, let's identify our variables. We'll use t for time in seconds and h for the diver's height in feet. The independent variable is time, and the dependent variable is height. What type of function best models the height of an object in projectile motion? The path of a projectile, like a diver, is a parabola. This means our model will be a quadratic function. The general form is h of t equals a times t squared plus b times t plus c. Now we use the information from the problem to find a, b, and c. We need to create a system of equations. The problem says the diver starts on a 20-foot platform. This is the initial height, which occurs at time t equals 0. So we have the point 0, 20. If we plug these values into our equation, we get 20 equals a times 0 squared plus b times 0 plus c, which simplifies to c equals 20. We've already found one coefficient. Now we know our equation is h of t equals a times t squared plus b times t plus 20. Next, the problem tells us that after 1 second, the diver's height is 12 feet. This gives us the point, 1, 12. Plugging this into our updated equation, we get 12 equals a times 1 squared plus b times 1 plus 20. This simplifies to the equation a plus b equals negative 8. We have one equation but two unknowns, a and b. This means we need more information to find a unique quadratic model. We need a third point. Here's where the physics of the situation helps us. In AP Physics, you learn the kinematic equation for position. The general form for vertical projectile motion is x of t equals 1/2 gt squared plus v0t plus x0, where g is acceleration due to gravity, v0 is initial velocity, and x0 is initial position. Let's apply this to our problem. We know the initial position, or initial height, x to 0, is 20 feet. So, our model is h of t equals 1/2 gt squared plus v by 0t plus 20. In the United States, the acceleration due to gravity, g, is approximately 32 feet per second squared, or negative 32 if we consider gravity pulling downwards. Let's use g equals minus 32. Substituting this in, we get h of t equals negative 16t squared, plus v versus 0t plus 20. Now we have our model, h of t equals negative 16t squared plus v divided 0t plus 20. We can find the initial velocity, v0, using the information from the problem. At 1 second, the height is 12 feet. So, 12 equals negative 16 times 1 squared plus v0 times 1 plus 20. This simplifies to 12 equals negative 16 plus v0 plus 20. Solving for v0, we get 12 equals v0 plus 4, which means v0 equals 8. Therefore, we have our complete model. The height of the diver at any time t is modeled by h of t equals negative 16t squared plus 8t plus 20. This is how we can construct a polynomial model using contextual clues and prior knowledge. Now let's move on to learning objective 1.14. B. Constructing rational models. Rational models are typically used to describe inversely proportional relationships. What does inversely proportional mean? It means as one quantity increases, the other decreases. A classic example is speed and time for a fixed distance. If you go faster, it takes you less time to cover the same distance. They are inversely proportional. These models take the form of y equals k over x, or y equals k over x squared. In other words, one variable is equal to a constant, k, divided by the other variable, or the other variable squared. The constant k is called the constant of proportionality. These relationships are very common in science, for instance in the laws of gravitation and electromagnetism, where force varies inversely with the squared distance. A key feature of these rational models is asymptotic behavior. As the independent variable gets very large, the dependent variable approaches zero. This is a horizontal asymptote. And as the independent variable approaches zero, the dependent variable tends towards infinity. This is a vertical asymptote. We can see this in the graph of y equals 1 over x. Notice the axes act as asymptotes. When constructing these models, it's crucial to identify this asymptotic behavior from the context of the problem. For example, in physics, it's impossible for a distance to be zero, so the domain must exclude x equals 0. A distance cannot be negative either, so the domain is usually restricted to positive values. Let's look at an example of constructing a rational model. Suppose we have a fixed volume of 1,000 cubic centimeters in a rectangular box with a square base. We want to find a model for the surface area of this box as a function of the side length of the base. First, let's write down the formulas for the surface area and volume of such a box. Let x be the side length of the square base and h be the height. The surface area, SA, is the area of the two bases, which is 2x squared, plus the area of the four sides, which is 4 times x times h. The volume, V, is the area of the base times the height, so x squared h. The problem states the volume is fixed at 1,000, so we have V equals 1,000 equals x squared h. We need to express SA as a function of x, not h. This means we must eliminate h from our surface area formula. We can do this by solving the volume equation for h. If 1,000 equals x squared h, then h must equal 1,000 divided by x squared. Now we can substitute this expression for h into our surface area formula. The surface area, SA, is equal to 2x squared plus 4x times the quantity 1,000 over x squared. Let's simplify this. The 4x in the second term will cancel one of the x's in the denominator, leaving us with 4,000 over x. So, our final model for the surface area is SA equals 2x squared plus 4,000 over x. This is a rational function, as we have a term with x in the denominator. Notice the asymptotic behavior. As x gets very small, the 4,000 over x term gets very large, and the surface area increases without bound. As x gets very large, the 4,000 over x term approaches 0, and the area approaches 2x squared. The domain is restricted to x greater than 0, since side length cannot be negative or 0. We have constructed these models, but what's the point? This brings us to our final objective, 1.14. C. Applying models. The whole goal is to use these functions to answer questions, make predictions, and understand how things change in a given context. We can use our model to predict values. For example, for the box problem, we could ask, if the side length x is 5 centimeters, what is the surface area? We would plug 5 into our surface area model. SA of 5 equals 2 times 5 squared, plus 4,000 divided by 5, which gives us 50 plus 800, for a total of 850 square centimeters. We are using our model as a predictive tool. We can also use models to find optimal values. For instance, what side length x would minimize the surface area of our box? Minimizing surface area would save on materials. Using a graphing calculator, we can graph our surface area function and find the local minimum. It turns out the minimum occurs at x equals the cube root of 1,000, which is 10 centimeters. So a 10 by 10 by 10 cube would minimize the surface area for that volume. Furthermore, we can analyze rates of change. What is the average rate of change of surface area between x equals 2 and x equals 4? We calculate the change in SA divided by the change in x. The average rate of change is 1,000 square centimeters per centimeter. This means, on average, for every 1 centimeter increase in the side length in this interval, the surface area increases by 1,000 square centimeters. And it's critical to include appropriate units in all our answers. For surface area, that's square centimeters. For rate of change, it's square centimeters per centimeter. This gives meaning to our numerical results. Let's quickly review what we've learned. We saw that our skill focus was on constructing new functions from context. We learned how to build polynomial and piecewise models by using contextual clues, transformations, or technology to fit data. Then, we learned how to construct rational models to represent inverse proportionality, paying special attention to asymptotic behavior. Finally, we explored how to apply these models to answer contextual questions, make predictions, and find average rates of change, always making sure to include units. Mastering these techniques is a key step towards understanding how mathematics is used to describe and solve problems in the real world. Let's wrap up with one more quick application. Consider a manufacturer who determines that the cost C in dollars of producing X units of a product is modeled by a piecewise function. The function is C of x equals 100 plus 5x for x less than or equal to 100, and C of x equals 1000 plus 4x for x greater than 100. This model shows a volume discount. For the first 100 units, each unit costs $5 to produce after an initial fixed cost of $100. For units after the 100th, the cost per unit drops to $4, but the fixed cost is higher. Let's find the cost of producing 50 units. Since 50 is less than 100, we use the top piece of the function. C of 50 equals 100 plus 5 times 50, which is $350. The average cost per unit is 350 divided by 50, which is $7 per unit. Now let's find the cost for 150 units. Since 150 is greater than 100, we use the bottom piece. C of 150 equals 1,000 plus 4 times 150, which is $1,600. The average cost per unit is 1,600 divided by 150, which is approximately $10.67 per unit. Why is the average cost higher for 150 units despite the discount on later units? It's because the fixed cost component for the higher volume is significantly greater. This shows how important it is to analyze the full model when making business decisions. Finally, let's take a quick look at how you might use regression on technology. Here is a scatter plot of some data. Looking at this plot, we can see the points roughly form a curve that first goes up and then down. This parabolic shape suggests that a quadratic model would be a good fit. We could perform a quadratic regression to find the best fitting quadratic equation. Alternatively, if our data looked like this, rising slowly at first, then more quickly, we might suspect it represents exponential growth. In this case, an exponential regression would be more appropriate. A linear model would not fit this data well at all. The key is to look at the pattern of the data and choose a function family that seems to match it. Once you have the regression equation, it is essential to look at the residuals, which are the differences between the actual data points and the values predicted by the model. A residual plot, which plots the residuals against the independent variable, helps you check the quality of your model. A good fit will have a residual plot where the points are scattered randomly with no clear pattern. If you see a pattern, it means your model isn't capturing the full complexity of the data, and you should try a different type of function. Thank you for watching. Today, we've equipped you with powerful tools for creating and applying function models to real-world scenarios. Keep practicing these skills, and you'll be well prepared for any modeling challenge. Here's a quick summary of the key concepts from this video. We can construct models by recognizing parent functions, which includes linear, quadratic, cubic, quartic, and rational functions. We can use contextual clues like zeros, asymptotes, and rates of change to determine the best model type. We can use technology to perform regressions on data and analyze residuals to assess the fit. Finally, we can use the models we create to make predictions, find optimal values, and analyze rates of change, always remembering to include appropriate units in our answers.